Welcome back everyone to another video in our FE Civil Preparation course. In this video, we are going to talk about torsion in thin-walled shafts. In our last video, we discussed the concept of torsion moment and torsional stresses in solid and hollow sections. However, we mentioned that these rules apply only in thick-walled sections. So what about thin-walled sections? First, let's identify thick and thin sections. For circular hollow sections, it is considered to be thin when the thickness of the wall is less than 1/10 of the radius, and it is considered to be thick when the thickness of the wall is over 1/10 of the radius. In case of irregular shapes, an average radius should be calculated. However, in FE exam, they will clearly mention in the question if it is thin or thick-walled section. So here, if we have this hollow section shown in the right, and it has been mentioned that it is a thin-walled section, and let's consider a torsional moment of T is applied on this shaft. In this case, there are two values to be calculated. First is the shear flow inside the walls, which is calculated by the equation of Q equals T over 2 AM, where Q is the shear flow, T is the torsion moment, and AM is the area of the section till the center of the outer walls. The other value to be calculated is the shear stress, and it is calculated by the equation of tau equals T over 2 AMT, where T is the thickness of the outer wall. So now, let's have an example of this.
So let's check this example. We have a thin-walled shell shaft, as we can see here, with wall thickness of 12.5 millimeter, and it has a torque of 280 Newton meter going around it, and we want to calculate the torsional shear stress in the shell wall. Okay, so we know that the equation of the shear stress due to torsion equals T over 2 area median multiplied by T. This is in case of thin wall shafts, as we have already discussed in this video. So let's start first by drawing our section here. Let's show the wall thickness, because now we want to calculate AM, which is the area median, and I want to show you how to calculate it. We want to calculate the area till here, which is the center of this wall. I will tell you another trick after we finish the calculations first. So now I want to calculate the area inside this dotted red line. I will calculate the area per each shape separately. I will calculate first for this rectangle, then I will calculate for this rectangle, then we'll calculate for this half circle. So we will say that area median equals to 300 minus 12.5, which is the wall thickness, multiplied by 260 minus 6.25, because this time we have half wall thickness only from one side. This is the first shape, this is plus the other rectangle, which is 300 multiplied by 150 plus the area of half circle, which is pi d square, and d square here is 150 square over 4. This is the area of a circle. Again, we'll divide it by 2 because this is half circle, so it will be over 8. Solving this equation will result on total area of 0.12 meter square. So tau will equal to 280 multiplied by 10 power minus 3, because we want to use the torsion per kilonewton instead of newton. So we multiply by 10 power minus 3 because we have all the result per kilopascal. This will be divided over 2 multiplied by 0.12 multiplied by 12.5. This is the area and this is the T, which is the thickness. We multiply again by 10 power minus 3 because we want to transfer between the millimeter of the T, which is 12.5 millimeter, 2 meter. So solving this equation, it will result on 93 kilonewton per meter square, which is kilopascal. So the answer is number D, which is 92 kilopascal. So the trick I wanted to tell you about, let's check the options here of the answers. We have 14 kilopascal, 44 kilopascal, 59 kilopascal, and 92 kilopascal. We can notice that the difference between these values are very big. We can't find any close values. And let's check now the area median that we calculated. We were calculating the area of this shape here between this dotted line, and it actually took from us some time to exactly calculate the median and to deduct the width of the wall, and when to deduct the full width and when to deduct only half of the width. This took from us some precious time. It will be very valuable in the exam. But if you notice that if you calculated the overall area, actually the difference, it will be very minor. We are talking about maybe like 2, 3, 5% increase in the area, which overall in the end was going to result in you like 5% or something increase on the result. So if you found that all the results are very close to each other, okay, then in this case you had to be very accurate in your calculations because you want to result on the accurate results. But in this case, in the exam, I was going to calculate the overall area. It was going to save for me maybe like 1 minute or 2 minutes, but it is very valuable. And instead of reaching 93 kilonewton per meter square, I was going to get a little more area. So the result here, maybe it was going to be like 91, 91.5 or 90.5 kilopascal. Again, it will be very close to the 92, so I can understand that this is the correct answer. Because I can see that the other answers are very far from each other. It is very important in the exam to note these issues, because you don't want to waste any time in the exam because it is already very stacked and you have very limited time for each problem. So this is it for our video today. Thank you.